Hello and welcome everyone to Dr.RAJESH'S Biogenesis. In this session, I will discuss about the basics of coordination chemistry and I will give you a classification related to ligands where you may not have seen the different types of the ligand classification. This is for the first time you are being provided with different types of ligand classifications. Well, when it comes to transition metal chemistry, two things will form the complexes. One is the central metal atom or the ion, and later on the ligands that are surrounding the central metal atom or the central metal ion. When I say that a ligand is surrounding the central metal atom or the ion, what exactly is a ligand? This is a term that was coined by a scientist, Alfred Stock, from the word called as ligare. Ligare means to bind. Finally, it has converted into ligand. So, ligand could be an atom or it could be a group that will coordinate to the central metal atom or the central metal ion. There are different types of ligands and the basic classifications that you are aware of. First, I will start with the basic classifications, then I will discuss different types of ligand classifications. The basic classification is based on charge. How can we classify the ligands based on charge? Well, based on charge, we classify the ligands as negative ligands, neutral ligands, and positive ligands. This is one type of classification, the basic ones, which many of us know. Based on charge, I can classify the ligands into three types. One, we call it as a negative charged ligands, neutral ligands, aqua, amine, and there are also plenty of other ligands such as phenanthroline, bipyridine, bipi, we call it as. Later on, we have positive ligands, very few number. So, the more number of ligands will be with negative charge. Some of them will be with neutral charged, very few with a positive charged. This is one type of classification. Second type is based on ligand strength. Based on the strength of ligand, I classify the ligands into three types. The first one is ligands that we call it as weak. Interactions will be very weak, moderate, and the third type is strong. This is a second type of classification. We can classify the ligands based on their charges. We can also classify based on the ligand strength. I will introduce a new one. Jorgensen classification, which is also based on the ligand charges, but this is a different type of classification. According to this, Jorgensen has classified ligands into two types. One, he called it as innocent ligands and non-innocent ligands. Every chemistry student is very innocent, as we say. So, just in a similar way, ligands are classified into two types. One is called as a innocent ligand, the another one is a non-innocent ligand or a suspect ligand. Suspect, you can suspect it. For what do you suspect? Suppose if I choose a ligand such as NO. Let me choose a ligand like NO. On the other hand, let me choose a ligand like a halide such as Cl minus or F minus, so on. If any ligand allows the oxidation state of the central atom to be defined, such a ligand we call it as an innocent ligand. Imagine if I am choosing Fe F6 3 minus. What is the oxidation state on iron? Straight away I can say that the iron has an oxidation state of +3. Iron is in 3 oxidation state. It is just because fluorine, whenever it is present, it is always found to be having a -1 charge. So innocent ligand is that ligand which will allow the oxidation state of the central metal atom to be defined. On the other hand, what is a non-innocent ligand means? It is that ligand which will not allow the oxidation state of the central metal atom to be defined. Suppose if iron is present with some other ligands along with NO, then I will ask you what is the oxidation state of iron, provided the oxidation state of ligand is given to you. Then you have to suspect, because once NO is present, NO could be present as NO plus or it could also be present as NO minus. So we have to always suspect such type of ligands. Even when oxygen is present, we have to suspect its oxidation state, because when oxygen is present, it could be present as superoxo or it could also be present as a peroxo form. Oxygen is also considered as a suspect ligand, non-innocent. NO is also considered to be a non-innocent ligand, but halides, hydroxo, once they are present, I can definitely give the oxidation state of the metal without any ambiguity. This is third type of classification. Another type, which is a basic one, but I will introduce new concepts in it. Based on denticity. How many donor atoms are present? Let it be monodentate, bidentate, tridentate, tetradentate and so on. So based on denticity, we can classify the ligands into two types. One is monodentate, another one is polydentate. Monodentate and polydentate, where there is only one donor atom, more than one donor atom from a corresponding ligand. For polydentate, I am classifying it into two types. One, I call it as acyclic, the another one is cyclic. So according to denticity, we are classifying them into monodentate and polydentate. Polydentate is being again classified into acyclic and cyclic. Cyclic could be monocyclic and polycyclic. There could be only one cycle or there could be many. One of the best example is a macrocycle. (18 crown 6). It is a 18 crown 6. Then comes to a polycyclic one. For polycyclic, you can choose an example of cryptands. What are cryptands? Means these are cryptate ligands where there are more than one cycles. Macrocycle 18 crown 6, it is single cycle, whereas this one is polycyclic. So the simple representation that is shown is this. This is only a ligand representation, one cycle. In this case, it could be many. And the donor is represented by a small circle. Okay, within this macrocycle, there could be some donor atoms. It could be 4, 5, 6. There should be at least a minimum of 3 donor atoms to be called as a macrocycle. For cryptand, it could be a 111 cryptand, 221 cryptand, 222 cryptand, or 333 cryptand, and so on. So that is for cyclic. When it comes to the acyclic one, we classify them into linear, branched, podal, and rigid aromatics. What exactly do I mean by this? Linear means the simple representation is this, where this is considered to be a donor atom. The simplest of the examples for linear is ethylene diamine. You can take an example of ethylene diamine. So this comes under a linear type of ligand. Branched one, you could have some branches, and one of the best examples is EDTA. EDTA can be taken as a branched acyclic polydentate ligand. Podal means, poda, it is just like some suspensions. Suppose if there is a base from which some ligands are suspended, such type of ligands we call them as podal ligands. I am taking a cyclohexane. This you can take it as 135 triaminocyclohexane. Okay, so this is one of the podal ligands. And finally we have rigid aromatics. The best example that we chose right. So different types of ligands can be taken and we can classify them into various types. This is one classification. Based on denticity, we have monodentate and polydentate. Within polydentate, we have acyclic and cyclic. Within cyclic, macrocyclic or polycyclic. Macrocyclic, best example is not macrocyclic, monocyclic. In monocyclic, macrocycles are the best examples. Within acyclic, linear, branched, podal, and rigid aromatic. So there will be a base through which the donor atoms or the groups will be hanging that can directly bind to the metal. And rigid aromatics, it could be like phenandroline types of ligands. I'll give you a couple of other modes. Based on bonding mode also we can classify the ligands. One type of classification is terminal and bridging. So the ligand could act as a terminal ligand or the ligand could act as a bridging ligand. We generally come across in biocoordination chemistry or organometallic chemistry. Terminal means if at all I choose metal, this is a carbonyl which you call it as a terminal bonding. Bridging bond, if CO is present, that can bridge two metals, or sometimes if there is a third metal, it can also bridge the third metal. So bridging is again classified into doubly bridging, triply bridging, or even quadruply bridging. doubly bridging, triply bridging, or even quadruply bridging. This is one type of ligand classification. On the other hand, based on bonding mode, we can classify it into end-on, edge-on, and side-on. Suppose I choose dioxazine as a ligand. For this dioxazine, these are the ends. This is one end, this is another end. These are the sites. And this one is an edge. If any metal atom comes and binds at these ends, you call it as end-on bonding mode. When it comes and binds to this, you call it as a side-on. And when it comes and binds here, you call it as a edge-on binding. Again I am showing end-on. Imagine that this is a metal, end-on, end-on. Two metals can come. Side-on, side-on. Two metals can come, one or two. And edge-on, only one is possible. Within this end-on, as I told you, when one metal comes and binds, you call it as end-on terminal bonding mode, or it could be end-on bridging. This is end-on terminal. This is end-on bridging. I need not put a double bond. Multiple bond has no relevance once I am showing a general representation. This is edge-on. Again for side-on, one metal can bind, two metals can bind. When one metal bind, you simply call it as side-on terminal. When two metals bind, we call it as side-on bridging. Side-on terminal, side-on bridging. Suppose if I put an oxygen, metal atom comes and binds to one side, it is terminal, side-on terminal. And that is called as a side-on bridging, where two metals are being bridged by this ligand. This is another type of classification. This is based on the bonding mode. There is another important type of classification which is based on the orbital overlap interactions, and you come across in the crystal field theory, molecular orbital theory, crystal field theory. You can see it in the spectrochemical series. Based on orbital overlap interactions. Sigma base, pi base, and a pi acid or pi acids. Sigma base, or I can call it as a sigma donor ligand. Pi base or a pi donor ligand. Pi donor will also be a sigma donor. Along with sigma donation, it is also donating pi, therefore you call it as a pi base or a pi donor. Pi acid is a pi acceptor. It means it will donate sigma, along with that it is also accepting pi. You call it as a pi acceptor. Look at the orbital overlap interaction. Suppose if I put a metal, ligand is also present. Now it is donating. This is a simple sigma bond. Such type of ligands are called as sigma bases or sigma donors. Next one is two different orbitals that I have chosen for the metal. This is donating its sigma. It is called as a sigma donor. Along with that, it is also donating pi. If this is plus plus, this is minus minus, plus and minus. Symmetry must match. Only then orbital overlapping interactions are possible. So this is acting as a sigma donor. This is also acting as a pi donor. Therefore, we simply call it as a pi donor ligand or a pi base ligand. Pi base is a sigma donor as well as a pi donor. So, you can represent this as metal double arrow towards metal. This is a case where there is a single arrow towards the metal. It is a sigma. This is a pi. Now, this can be represented with metal. One arrow towards metal, the another arrow towards ligand. One is a sigma, the another one is a pi. You just look at the qualitative difference. For the metal and ligand sigma, I am drawing with the same color. You look at the difference now. This is a ligand, there is also a ligand. In this ligand, if this is a p orbital, this is a p orbital, but this is a different one. In which way it is different means, if this is considered to be a bonding one, this is considered to be an anti-bonding one, which is accepting electron density from the metal. One is donating to the metal, the another one is accepting from the metal. So these are the ligands that are called as pi acceptors. The best example is a CO. The best example is a CO. It will have a pi star, not a p antibonding. It is a pi star antibonding. This one is a pi. The qualitative difference that you can see when I draw the lobes is the two lobes must be straight. They are just like linear related. Once it is a pi bonding molecular orbital. Once it is a pi antibonding molecular orbital, these must be bent. So once they are bent, it is certain that they are antibonding. Once they are bent, the orbital overlapping interaction will be very strong because they are very close. But in this case, they are like linear. So orbital overlapping interaction will be weak. This will strongly accept, and that will form a pi. And these type of ligands are called as pi acceptors. It is accepting into antibonding molecular orbital. So that will bring a lot of differences in the stretching frequency of carbonyl type of ligands, which are a very strong pi acids. This is one type of ligand classification based on orbital overlapping interactions. I can classify them into sigma base, pi base and a pi acid, out of which pi acid is the most strongest one. Then comes the sigma base, and the least stronger one is pi base. That is the least stronger one, or it is the weakest one. Whenever a pi acid is present, the splitting will be very large. So usually we get low spin complex. And whenever we have pi bases, usually we get a high spin complex. That is usually. There could be some exceptions also. Right, these are different types of classifications. Along with this, we also have some miscellaneous classifications. Miscellaneous means, suppose if I choose some other names like ambidentate ligands. What are ambidentate ligands? Ambidentate ligands means, ambi means both. So these are the ligands where the donor atom could change. One time if it is donating one donor, the other time depending on the interactions, it will give another donor atom. But at any time only one will act as a donor. Even if both can donate, when there are both two donor ligand atoms, only one of them will donate at a time. Such ligands are called as ambidentate ligands, because when both gives, that come under bidentate ligand. This is not a bidentate, this is ambidentate. Within this ambidentate, again we can classify them into two types. One is simply diatomic ambidentate ligand. The another one is a polyatomic ambidentate ligand. If I give Cn minus, or it could be Nc minus. So either carbon could be a donor or nitrogen could be a donor depending on the type of the interactions. It is a diatomic one. On the other hand, when I choose a polyatomic one, it could be 3, 4, 5 atoms, out of which 2 can act as donor atoms. So in the polyatomic one, donors are separated by single atom. Donors are adjacent. Let us take an example, then you will easily understand. Donors are separated by a single atom. Suppose if I take thiocyanate S or thiocyanate N, sulfur can act as a donor, nitrogen can also act as a donor, but at any time only one of them will act as a donor, either sulfur or nitrogen. Okay? And these are the two donor atoms which are separated by a single atom. So donor are separated by single atom which come under polyatomic ambidentate ligands. Now this is a ligand where the donors are adjacent. They are polyatomic but the donors are adjacent. Nitrogen can act as a donor, oxygen can also act as a donor, they are adjacent to one another. Such ligands we call them as ambidentate ligands. We have flexidentate ligands. Flexidentate ligands means it can change its denticity. Supposing that I give EDTA as an example or sulfate as an example. Sulfate can behave as a monodentate one or a bidentate one. It can give only one oxygen atom at a time, or it can bind with two oxygens and it can coordinate to the central metal atom. So 1 or 2, denticity is shifting. EDTA, it could act as a 4, 5 or 6 donor atom. So it is changing its denticity, and all such ligands we call them as flexidentate ligands. Bridging ligands, anyway we came across about these bridging ligands. They can bridge two metal atoms or the two metal ions at a time. Some ligands can also bridge more metal atoms. It could be triply bridging or it could be quadruply bridging. Finally, there is also ligand with cyclic perimeters. There are ligands with cyclic perimeters. Cyclic perimeters means, suppose I can choose ligands such as cyclopentadienyl anion, it is abbreviated as CP anion, or it could be a benzene, or it could be a tropylium cation, or it could be a cot dianion, cyclooctatetraenyl dianion. They can form sandwich complexes where you find it in organometallic chemistry. So ligands with cyclic perimeters is also one of the basic classifications of the ligands. All these are different types of ligands and all these come under coordination chemistry. Hope you like this classification because I have put all the ligand classifications at one point. Thank you.